So I'd like to introduce Ghislain and Ingo, who will be talking about Rumble.
Okay, cool. So my name is Ingo Mueller. With me in the call is Ghislain Fourny. We are both in the systems group at ETH Zurich, and we work together with Gustavo Alonso. And today I'm going to present Rumble, a JSONiq implementation that we wrote on top of Spark. And I'm quite excited to present this to you today for a number of reasons. So first, I'm excited about Rumble itself because we built a system that is actually useful. For better or worse, that's not necessarily typical for our community, where often we are content with showcasing a particular aspect of a system. But here we pushed it further and built a system to the point that people are using it and tweeting about it and blogging about it. So, and I guess that's an interesting aspect for me. I'm excited about talking to people to CERN today because for a while now I've been eyeballing at the data and analytics problems that you guys are dealing with, and I find them really interesting. You're one of the communities that really work with big data. Oftentimes I have found myself looking for a large enough data set to challenge the solutions that I'm building. And I guess that you guys don't have a problem with challenging my solutions. And this leads me to the last point why I'm really excited about. We think that Rumble could be useful for analytics of physics data today. And while this is our outside view, what really the purpose for me, for us today is to get your view on it, who know about these problems much better. So while I'm going to do what looks like a lecture, it's really a long way of asking the question, what do you think about Rumble as a system and JSONiq as a language? And I would lead you to the system a bit, how we came there. Ghislain and I are both teaching together the big data course here at ETH. Ghislain's the lecturer, I'm organizing the exercises. And we realized in the chapter when we're dealing with semi-structured data similar to JSON, that there is no good system out there that does that at scale. And Ghislain, with a couple of students, decided to change that and build what has now become Rumble. So I'm going to lead you to this project a bit like we are explaining it to the students in order to know what mindset we had when we built the system, and such that we know what it's able to do today. My slides are not here. So I start with a very brief overview of big data at the risk of preaching to the choir. So we think of big data as big in 3 dimensions. It's big in volume, big in variety, and big in velocity. It's big in volume just by the sheer size, by the amount of bytes that we are storing, which has reached scales that are difficult to imagine and maybe only present in physics other than in this domain. Data has also increased in variety, and we tell the students that even though there is a lot of variety, it really boils down to 5 fundamental data shapes. One is completely unstructured data in the form of text, then more structured data in the form of graph, or in form of cubes, in form of tables, or in form of trees. And this will be the topic, this will be the data shape that we look in today. With trees, we refer to arborescent data that typically occurs in documents. And finally, data is big in terms of velocity, and we think of this as really 3 related factors: the capacity and the throughput and the latency of the underlying storage media. So if you look at the first commercially available hard disk drive, it could only store a couple of megabytes, and today it can store an enormously large amount of data. I'm actually showing the largest, or one of the largest drives available today already, and only by zooming out we see how small they are today compared to the previous one. However, they can store a huge amount of data. To put in numbers, from the mid-50s to today, the storage capacity has increased by a whopping factor of 200 trillion. And this dwarfs the other improvements, which are still several orders of magnitude at least. In this plot, we see already the throughput and latency improvements on a linear scale, and they are barely visible. We need to go to log scale to show them. And this plot is really the fundamental motivation for the entire big data lecture. This different speed by which storage, different aspect of storage has improved. And it's fundamentally because it explains why the systems that are built for big data analytics are built the way that they are. They are based on parallelization in order to come the discrepancy between capacity and throughput. Because a single drive has increased capacity much more than it has increased throughput, we now need to read from different drives at the same time in parallel in order to get to read the data that we have reasonably fast. And similarly, we can't afford many round trips anymore because latency hasn't kept up with the throughput. So what we need to do is fetch the data in batches, and this explains why all of the big data processing that we're doing are systems that do parallel batch processing. So I mentioned briefly that we think of JSON as tree-shaped data, and that's true for other denormalized data shapes. And I want to bring everybody on the same page of what we mean by that. We contrast that in our lecture with what the good old databases, so to say, do, and that's really what we teach to the bachelor students when they do computer science. We tell them to avoid redundancy at almost all costs by bringing the data into normal forms and then connecting them through foreign key relationships. The problem is that in many situations, the real world isn't quite like that. There are cases where these normal forms don't really fit or don't really fit yet. And another problem is that joins are expensive. And that's not only in terms of computational requirements, but also in terms of management and mental effort to deal with data when we need to join them. So what tree-shaped data does instead, it represents everything denormalized. That's one thing. Furthermore, it gives up even the first normal form. We allow now non-atomic values, namely nested values, inside of our tree-shaped data. We allow missing values. We allow invalid values in the sense that we allow values that that have a different type than the usual type of a particular attribute, and we allow extra values that may have gotten there accidentally, but that we don't want to discard just yet. And if all of these aspects are present, we think of data as tree-shaped data or nested heterogeneous data, as opposed to the flat homogeneous data that we normally deal with in tables. JSON is one of these data models that allows to store data of that shape, and it has a really simple model. One aspect, it has 4 atomic types and 2 types to nest these. Arrays, which can store a sequence of values, not only homogeneous sequences like the 2 strings here, but really any sequence of values, and objects, which are mappings from strings to any other values. And this is, while it's extremely simple, it's also extremely powerful, because you can combine objects, atomics, and arrays in many different ways, and this way essentially model anything that more specific data models could also model. A very related concept is that of JSON lines files, which usually which store 1 JSON value per line, which are usually somehow connected to each other. I will go into this detail a bit more below. And now, in order to be able to deal with humongous amounts of these trees, we need a technology that can do that at scale, and the one that we have decided to use here is Spark. So I will do the one-on-one primer. Excuse me if you apologies if you have if this is repetition for you. I'll be quick. So we think of MapReduce as a we think of Spark as a generalization to MapReduce, which consisted of two faces, map and reduce, and which Spark generalizes to arbitrary DAGs. DAGs are built around these resilient distributed data sets, or RDDs in short, which are really just partition collections of values. And the way to formulate computations in Spark is to create some RDD, typically by reading from a file, then producing a chain of lazy transformations until eventually an action triggers the computation of these different transformations and returns the result to the user. There is quite a large number of transformations built into the system that people can use and combine to formulate their computations. And the one example that I want to show here is the Hello World program of big data analytics. It's word count, and we use here the parallelize function that creates an initial data frame, an initial RDD from a list of strings, then uses the flat map transformation which is parameterized by a function that splits each of the input string by a space, returns several values which are flattened by flat map, and the individual strings produced here can then be counted, and that produces the word count result that we wanted. One very quick distinction of Spark compared to data stores or database systems: Spark is meant for read-intensive or maybe even read-only workload. It's batch processing where no ETL process is required because we can read the data as it is stored in the file system. And that's opposed to data stores, which are usually focusing on transactions that should be executed at a low latency, and that often require an ETL process in order to load the data. Somehow the logical follow-up of Spark was to introduce data frames and run SQL on them, and I want to discuss this because it's something that we also use in Rumble, and that also illustrates an important question, that an important aspect, another important aspect. This aspect is data independence. So data frames are a logical data model that allow users to look at data, think of data, and manipulate this data independently on how the physical storage, how that data is stored physically, and how the manipulations are carried out. So what this illustration here in the lower half of the slide should show is that typically data is stored on a file system somehow, but it could be on really any storage medium. It could be clay plates if we want it. It could be an Excel data sheet. It could be physically stored on one single hard disk drive, or it could be stored on a cluster. It could even be stored on DNA, and that's not a crazy idea that we are imagining. People have actually encoded SQL relations as DNA, and they have encoded SQL analytics as chemical reactions on top of DNA, and they're able to run their SQL queries in that DNA database. So in short, what data frames are allowed is to store related data in a data set which is really just a collection of rows, and more precisely, rows consist of attributes. So we can think of, this is why we can think of relations as tables that have different columns for the different attributes. And what is nice about this is that we can use a high-level declarative language such as SQL and run SQL against these data frames, and behind the scenes Spark does its thing to whatever it needs to carry this out, and we don't need to think about how that works. The problem for the use case that we had in mind, remember it's heterogeneous arborescent data, is that this doesn't really fit into data frames. And there are a number of problems. One is that here in this example where we store these persons, there are most of the persons, their name is composed as a first name and last name, and then there are a few who only consist of a string. So the database system can't really store that as a data frame because it needs to find one common type of them. And we see something else here. Instead, most people represent the countries they have been as an array of strings, and then there are a few individuals that where they have only been in one country and they have one string in that place. So if we run Spark natively against a data set like that, what it does, it exposes the things that it doesn't understand, or the things that are heterogeneous as strings, and it leaves it up to us to open up these strings and analyze them by manipulating the strings directly. Now, to some degree, there are solutions built into SQL-like languages or proto-NoSQL languages. For example, if we have homogeneous arrays, then extensions to SQL actually allow to manipulate those. There's, for example, this explode functions that unnest the elements inside of the arrays as new rows, such that we can manipulate those with the normal SQL primitives that we have. Similarly, there are methods that we refer to SQL with dots that allow us to access attributes of object type columns and extract them as atomic columns and deal with them that way. So even though that exists, we still argue that data frames are not the right representation for the tree-shaped data that we have in mind. And of course, we think that we know a solution. There's this language called JSONiq. Ghislain was actually involved in creating the language. And JSONiq is a language that was created for exactly that, for exactly the problem that we have in mind, analyzing JSON data with all of the intricacies that it has. And in order to do that in a reasonable way, it has a data model that is able to represent everything that can happen in JSON, really. And this is a really central concept. In JSONiq, everything is a sequence of items. So a single string is a sequence of one item, which is a string. If you don't have any value, then you represent that as an empty sequence. You can have sequences of integers, of booleans, of objects, of arrays, or you can have completely mixed type sequences. All of that is possible, and it's all possible under this one concept of sequences of items. And since everything is in a sequence of items, all expressions work on sequence of items. And that starts with arithmetics. The arithmetics that normally manipulate numbers in JSONiq manipulate sequences of items with the restriction that they only work on sequences of length 1 or 0. They treat the sequence of 1 as the normal as a single number. So if we work on two sequences of length 1 both, then arithmetics has the normal semantics that we're used to. But there's an additional capability of dealing with absent data through empty sequences. And really, all of the other expressions that also exist all of them take sequences of items as input and produce sequences of items. And this means that we can literally put any expression as an input of any other expression. And while I don't want to explain the whole query that we are looking at here, I want to take it as an example. We have this large flower expression that I will explain in more detail in a minute, that produces some sequence of items, which is fed into the count function. And the count function counts how many items there are in that sequence, returns a sequence of one item that represents that number, and finally the plus expression adds the literal 2 on top of it. So I promised that I will explain the flower expression in more detail, and it's actually a very important expression in JSONiq. It's maybe the most powerful expression. It essentially does everything that SQL select from where does, and a bit more. So in particular, here to start with the top left example, the for clause allows to iterate over some sequence of items and bind them to a variable, such that later clauses, such as the where clause here, can refer to these items in the through the variable. With that, we can express filters in the where clause. We can express projections. Here it's done through a function call that returns a new object where all members of I have been removed except countries. There is a group by clause that is very similar to what group by means in SQL. All tuples that are passed from the previous clauses to the group by clause are grouped by the value that a given expression produces, and then later clauses can refer to the grouping variables, which are now all sequences of 1, and through the non-grouping variables, which now contain the sequence of all values that belong to the same group. Finally, it's possible to do joins just by having several for clauses which initially produce the Cartesian product, at least semantically, and then have an equality filter such that this becomes a join. And essentially these clauses, unlike SQL, and that's why it's more expressive, these clauses can be repeated any number of times and in almost any arbitrary order. So we see here that we can have for clauses, order by clauses, and then later again a for clause and a where clause. That's something that in SQL is much more cumbersome to do. The semantics of flower expressions is defined by a concept that is called Tuple Streams, and I need to describe this a bit because it will be important later to understand how we execute these flower expressions. So each clause produces one of these tuple streams, where tuple is simply a binding of variable names such as I to their values. So the for clause produces a tuple stream of tuples that only have one variable, and each of the items in that input sequence is bound to I in one of these tuples. The let clause can read these tuples and adds another field here, name, based on the values that is where the value is given by the result of this expression, and the where clause can now consumes tuples that both have I and name, filters out some of them, and the return clause consumes them, and eventually transforms these tuples back into an item, because remember, any flower expression only produces sequences of items. So any consuming expressions that are not shown in this example expect items, and that's what a return clause does. Okay, so hopefully I have given you some idea about why we have been building Rumble, what the problem of heterogeneous nested data is, and how JSONiq works. So now I'm going to present what we actually did about all this and how we build Rumble. The architecture overview is really simple. The user only really sees JSONiq as a query language, and we have put some logic in place to map that onto primitives in Spark. And Spark executes, so Spark is able to execute these queries in a cluster. And usually Spark reads from a distributed file system such as HDFS, but really in JSONiq we can read whatever Spark can read, being a database system, a cloud storage, whatever, local file system, whatever it is. Typically the input is a JSON lines document, a bit like this one shown here, but usually larger. But we've extended Rumble with the ability to read from other formats as well, including Parquet and also Root since a few weeks ago. Rumble shows itself to the user as through a prompt at the moment. So the user gets a shell where they can write queries, a bit like the query shown here. Hits enter and then gets presented with the result. And so this is how the user perceives this. What is interesting for us is how do we make this happen? And I need to explain a couple of things now, how the JSONiq constructs map on the primitives that Spark offer. And what I will start with is how sequences of items are mapped. Remember that this is a very essential or the only way to store, to represent data. And it's actually rather simple. So we have this polymorphic base class item that we implemented in Java, and where the concrete types, the six types that I showed you in the beginning that exist in JSON, inherit from. So we have 6 concrete classes that all inherit from item, and we just store these in an RDD. So this is a very easy way to represent sequences of items. And we do something very similar with the tuple stream. So in addition to RDDs of items, we can also store RDDs of tuples, where tuples, as you imagine, probably are mappings from variable names here, I and name, to values, and they can also be stored in an RDD. And now for the different expressions and for the different clauses, we need to define we need to map their semantics into a sequence of transformations in Spark. I will do this here for the group by clause, but the other clauses and expressions are really similar, and there's some more detail in the preprint that is linked to at the end of the slide, at the end of the talk. So in short, what we do for the group by clause is to compute the grouping values, then use the built-in group by functionality of Spark, and finally do some post-processing. In a bit more detail, we use map in order to produce this pair RDD, where the key becomes the value by which we want to group. Here it's the name variable defined just in the previous clause, and the remaining tuple or the whole tuple as a value in that pair RDD. We can then just call the group by key transformation of Spark and end up with a grouped RDD where our grouping variables in JSONiq correspond to the grouping variables of the RDD, and we have sequences of tuples or groups of tuples for each of the groups. We need to post-process that with a map function in order to get a sequence of items for each of these variables. So now, while here we have a sequence of tuples, here we have a tuple of sequence of items. And after that, this RDD is given as an input to the next clause, which does something similar according to its own semantics. Okay, what I will do now is walk you a bit through the flow of one query. And the query is, and this is really a relatively standard architecture. A query starts as a string that is read by a parser and transformed into an abstract syntax tree. That is translated into an expression tree. And finally, a query compiler generator produces an executable form of that query, which is a tree of runtime iterators that can eventually be executed. And while this is a standard thing to do for query processing systems, let me emphasize that this is really how data independence is achieved by query processing systems, because there is all of this transformation machinery. The query language does not need to reflect in any way how things are eventually executed. And SQL is a good example, but also JSONiq is a good example, because there are other JSONiq implementations that can run exactly the same queries on a single node, and Rumble can run the same queries unmodified on a Spark cluster. So the query itself does not encode in any way where the query is eventually running. So what I will talk about now is how these iterators, how these runtime iterators really look like. And since I told you that there are two concepts that we need to deal with when we are executing queries, items and tuples, which are used between expressions and between clauses within a flower expression, respectively. We also have two types of iterators, and I want to show this on an example. Here we have this relatively simple flower expression that reads the items from this JSON lines function, which produces a sequence of items. And the different types of iterators are used like indicated in the colors here. The JSON line function produces, as I said, a sequence of items that's indicated by the orange arrow. And then within between the clauses in the flower expression, these clauses communicate with tuples. And finally, the return clause consumes tuples but produces items and uses the item iterator interface in order to produce its results. Another interesting aspect is that this subtree here, which corresponds to the predicate in the where clause, is executed several times, namely once for each input tuple. So what our iterators need to support is to re-execute a plan like this. Now we had several options for implementing these iterators, and one possibility is to materialize everything inside of each iterator. So for example, this for iterator could consume one element at a time and reading all available input in order to produce in one go its output. And while this may make sense in some situations, it often consumes too much memory. So we decided against this way of executing. And what we do instead, in many times, is a streamed execution. This is also known as volcano-style iterators in our field. And with that execution model, an iterator consumes one input tuple, does its computations, and produces, if possible, the output immediately. In particular, before moving on to consuming the next input, produce that output, consume the next input, produce that output, and so on. And this has the advantage that it has the lowest possible memory footprint, but it's also slow. It can be slow due to the function called overhead. And the way how we solve this for now in Rumble is just to parallelize execution. Both the tuple streams and sequences of items can be parallelized. They can be stored as RDDs. I told you that earlier. And these RDDs are stored on several machines, and the manipulations that Spark does on them is also done in parallel. So we can just take as many machines as required to speed up this process. There are other ways to speed up the process, which we will tackle in the future, but for now, this brings execution time into a reasonable range. So to tell you a bit now where the different execution models are used, they're actually both used. And in the same example that we looked at earlier, in the dashed lines here, we use this parallelized Spark-based execution, and that's because that's where most of the data is usually at. So the JSON line file that reads from the JSON line function, which reads from a file, usually produces a large output, which is why it produces its output as an RDD, and then the subsequent flower expression continues executing in RDDs. The computation that is done on each of the tuples is expressed with the other interface, the local interface, and that's given to the Spark primitives as a closure. And then similarly, the input here to the JSON line document, which is just a single string, is also a local computation, and then that it's really only after we're reading the large input that we use RDD style communication. This doesn't only work for flower expressions, as I showed here, but also for some other expressions, in particular the postfix expressions shown in this example. So here, the data produced by the JSON lines expression that is consumed here by the predicate expression that predicate expression can also be mapped to a Spark primitive and therefore run in parallel. And the same is true for that member lookup that you see here, as well as that count function that counts how many items there are. And to give you a bit of an idea where these iterators bring us in terms of performance, we compared Rumble on top of native Spark interfaces on some homogeneous data set. And it's maybe most useful to look at the group and sort microbenchmarks that we did and start with comparing Rumble, which is shown in blue, with Spark SQL, which is shown in yellow. And we see that Spark is about a factor 2 slower. And the way how we think about this is that this is the price that you need to pay for being able to deal with heterogeneous data. From an implementation point of view, this is due to the iterators that we are running inside of the Spark primitives, which is something that the user doesn't see. So these runtime iterators seem to have some performance overhead. However, keep in mind that this comparison is a bit an apples to orange comparison, because we have picked that homogeneous data set because that's the only thing that Spark can deal with. The reason why we build Rumble is to deal with heterogeneous data, which is something that Spark is absolutely not useful for. So the way how we think about this is that we, if you have a heterogeneous data set, you can deal with that in Rumble easily, and it's only twice as slow as Spark is. You could argue that using Python, the Python interface of Spark, PySpark, could be a reasonably easy way to deal with heterogeneous data, because JSON data maps to built-in Python types. So that's a reasonably easy way to deal with heterogeneous data as well. But as the green bars show, the performance overhead that you pay by using PySpark is actually much higher than that of using Rumble. Okay, and to wrap up, we have to say that Rumble is ready to use. We are using it for teaching. We have heard of other universities using it for teaching. And occasionally we see people tweeting and blogging about it and sharing that they have been used it for some work or some pet project that involves some sort of heterogeneous data set. There is an extensive and quite helpful documentation out there. I can praise the documentation because I've only used it and I haven't written it myself, but I found all of my questions answered there. And we also have a paper preprint on arXiv in case you're more interested in some of the details. And then on a very last note, to tell you a bit about the future plans that we have with Rumble, we have some smaller missing features. Many of them qualify as syntactic sugar, so we should be able to implement them with exactly the same techniques that I've presented today. We want to use data frames more than I have shown today, and that's something that I'm personally quite interested in. So in many cases, we actually don't need to deal with this heterogeneity because we know the types, either because we are pointing JSONiq to a fully structured format like Parquet or Root, or because we can infer types by how the query is dealing with the data. And if we know the schema and the types, we can actually we can map execution better to data frame and execute them more to data frames and make them and execute them more efficiently, or even map expressions to some other more performant frameworks than Spark. And we have started experimenting with MLAR, some compiler framework that Google made in the context of built in the context of TensorFlow, and our own framework called CVM, or Collection Virtual Machine. But that's a bit like roadmap for, I don't know, a couple of months to 2 years. And finally, we've started exposing machine learning libraries, specifically Spark's MLlib into Rumble. That was a masterpiece project just completed last week. So now you can use some of the machine learning algorithms from Spark already directly from within JSONiq. So this concludes my talk. I'd be happy to answer questions now and then hear what your initial thoughts are on Rumble and JSONiq in the context of what you're working on.
Okay, thank you very much for this wonderful talk. I'm going to let others ask questions first, because we're moving into this area. I'm sure there are a lot of people with questions.
I have, maybe, I don't know, the first one is regarding the implementation. Do you provide the Python interface? Because that's what we mostly use in the Spark, or it's mostly the Java-based one?
That's an excellent question. I haven't talked about this with Ghislain yet. But it's a question that I have started to think about. So I suppose that what would be interesting for you is to be able to send queries from a Python program to Rumble, right?
Well, we have a lot of Spark-based workflows, and for that purpose, we use a PySpark, which is by itself a thin layer on top of the Java libraries. So
right.
that's why, I mean, as far as I know, not so many people will go down to the Java level, but you may have more adaptation if you provide a PySpark-like interface or any other Python APIs.
Right. So what I think would be very well conceivable, let me go a few slides back. Sorry, this will just take a few, here. So almost the only interface that we have now is a shell like this. So there is no really programmatic interface to Rumble just yet. But I think that that would be an implementation effort of at most a few hours to have a function call, a function interface to which you can provide a JSONiq string, very similar to how you can provide a SQL string to Spark. And then I believe it would also be reasonable effort to expose that function in Python. And I think that that would make you much happier than having just this standalone prompt. Am I right?
Yeah, so that would definitely be helpful, because I mean, obviously, I'm very excited about this system, because we do have lots of unstructured nested metadata represented in JSON and with a large volume, but that requires, if we'd like to process those, we need to have a programmatic interface which we can integrate with existing workflows.
Right, right.
The second question I have, well, I just
have a few things on the first question.
Yeah.
I just wanted to add something on your first question. So first, we already have for Java an API. So there is an API that you can use in order from Java to call JSONiq with Rumble. And there are plans to try it with Python as well, as Ingo said. Then this interface works in the same way that you embed SQL queries, you can embed JSONiq queries. What we would like to have in the end is a way that you can, if you have a data frame or an RDD, that you can directly execute JSONiq from within PySpark. Another thing we are looking at is Jupyter notebooks usable with JSONiq. And lastly, I would also want to say that JSONiq is more powerful than just a query language. It has an update extension. It has a scripting extension like PL/SQL. So it has the potential of replacing a lot of things that Python already does. But of course, in the short term, for for acceptance and for people to use it, it will need to be integrated with Python. That's definitely the case. Yeah.
Well, but that brings me to the second question, which may be more interesting to solve all of this problem, because setting up the entire machinery on a Spark is quite a bit of work. Not only that, you need to have an infrastructure, you need to have the access, you need to have the tools, you need to have the dependency, libraries, etc. So this implies that harder and harder integration between the workflows we're running out of Spark and the workflows which require the Spark. And the certain bridge is actually go to the service-like implementation, where I can imagine that this JSONiq would be a simple service sitting on a Spark, which I can just query through the HTTP request, because it supports the JSON or whatever format the query would be provided. I mean, if it's a normal SQL-like interface, it's just the text, right? But I can assume that I can send a JSON as well. So this brings me to the second question. Do you consider providing the service-like interface with HTTP access and endpoints which people can use? And this interface can be, this service, I'm sorry, can be part of the Spark infrastructure, which will allow us basically to decouple this infrastructure from the normal workflows we're running outside of Spark. But at the same time, we can query it in a normal way as any other HTTP-based service.
Absolutely. That's something very natural to do. A lot of database products do exactly that. And providing access to Rumble via an API like HTTP or REST or something like that makes absolute sense. And so, of course, hearing you say that puts a +1 on it, basically. It's very informative to us to know that this is something you would enjoy having.
So I guess just to rephrase your question, if I understand you right, you would like to have something similar to a query as a service system, a bit like maybe Amazon Athena or Google BigQuery, if you know them, where users in your community can connect to in a local cluster and essentially just send a query, you get results back, and somebody maintains this cluster, and most users don't need to care how. Is that right?
Yeah, exactly. Because what we have two kind of use cases. One is like a Spark intensive workflows, which we run on the Spark, but number of people who have a knowledge of accessing and writing code at Spark is very limited.
Yeah.
On the other hand, we have a huge community of people, users. It's not necessarily physicists, but also, you know, people involved in the computing and infrastructure, in operation, etc., who are mostly interested in the aggregation of the results which we store on the HDFS. And for that purpose, I definitely see huge benefits of implementing the HTTP service-like functionality, where we can use any programming language. We can integrate it with the existing workflows easily because it's an HTTP interface, and we only care about, you know, the end results. How internally it's implemented, we will actually leave it to whatever the development team which will take care of that. So that would be a huge benefit, I would say, in integrating this into our infrastructure.
Right. So I think that I understand. I think that I understand, and I agree with the advantages of this kind of architecture. One interesting thing that comes to my mind is that if you have an architecture like that, in the long term, I think it would be a very good idea to have a high-level language. Maybe that is JSONiq, maybe it's something else, but it should be a standardized high-level language such that further down the road, as technology changes, you can change how that language is executed without changing the programs that have been written in that language. That's exactly the principle that data independence gives you, and which maybe suggests that this query as a service that you have in mind should not be tightly integrated into Rumble, but rather be orthogonal to it, such that maybe down the road you stop using Spark completely, you can use some other JSONiq implementation if it exists.
Well, yeah, that brings me to my third question. So, which is how relevant is Spark per se into the Rumble architecture? So, my understanding, you basically use it as a distributed engine for the calculations, but I mean, normal distributed system based, I don't know, on any other engine would probably work, which will just use the computing power. Not what I hear is this Spark is only helps you to do the parallel processing, right?
I guess yes. So definitely there can be other JSONiq implementations other than Rumble that run on some other framework. But I'd argue that Spark is a pretty well-suited framework because it has some very useful primitives built in that we can use. For example, we can use the grouping and the ordering that are provided natively by Spark in order to implement the pretty much equivalent functionalities in JSONiq. Okay,
so the final question, since I still keep asking there, you mentioned that the query language, it should be the implementation of the query language and the representation can be abstracted in such a way. Do you consider just use the JSON itself as a data format for the query language? Because majority of the document-oriented databases, right, like you mentioned Elasticsearch or something, they use underneath basically the JSON as the way to describe your queries.
Well, JSON alone is only a syntax, right? It doesn't. JSON alone doesn't formulate queries.
Well,
now this is a question for you, I think.
Oh, do you mean I should answer?
Yes, if you.
Yeah. So indeed, JSON is only a data format. It's not a query language. So JSONiq is a query language, and JSON would be like the tables for SQL. Now, JSONiq is a superset of JSON, meaning that any JSON document is a JSONiq query that outputs itself, kind of. Now, the internal storage, the JSON data model that is implicit from JSON is actually almost universal to many data formats out there. Parquet uses the same model, Avro uses the same model, Root uses the same model. So JSON is actually only one of the very many possibilities that you have to actually store it. There's a lot of document stores that, even though they use something that resembles JSON, they actually store it in a more optimized format. So this is really orthogonal. It's a little bit like a virtual machine where Spark acts as an assembly code or a CPU, but a CPU on a cluster. And on top of that, we have a data model and a language that are fully data independent.
Okay, thanks.
Hi, thank you for the interesting talk. I have a question, technical detail. Can you say how you connect to Root as a data source?
So we use the Laurelin, whatever you pronounce it, reader. And so syntactically, this is exposed to the user as a built-in function. Instead of saying JSON file like you see in the screen right now, you say root file, and you point to root file, and that behind the scenes uses this root file reader that is made available to Spark. And the same way, we can actually interface pretty much any Spark reader for other file formats, and we have done it for a number of them.
Right, thank you.
And then maybe a related question, maybe you had that in mind, maybe not. The question is how. One question to answer in that area is how does the root data model fit onto the JSON data model? So if you open a root file and just say if you just take root file parentheses and then that thing and then the path such that that function call prints you the content of the whole file, what you will see is that for one line, for one event, you will see what looks in JSON like an object, where the different values in the different columns, or branches, I believe they're called, are members of that object. And if an object is if one of these branches is a nested branch, I'm not sure whether I'm using this word correctly, but if something is an array type, a vector,
right,
then this is shown as a JSON array.
Yeah, this I can imagine quite well. This mapping is somehow natural, yes.
And then this is something that when you print it to the screen, it actually uses JSON syntax, but internally it has a more efficient structure for it.
Yeah, that's very nice.
And it supports many other. It supports many other types. It supports dates, times, date times, timestamps, hex binary, base 64 binary. I think there's almost 20 atomic types, and it's extensible.
I have a question. So in clouds, like Amazon Web Services, it has become rather popular to have in-place querying and storage. So like S3 select is a good example. Have you thought of when you connect to, I mean, you seem to be mostly based on files, but you have also interfaces to buckets, and particularly also buckets or other storage forms where you can push down selections, for instance, like for instance S3 select. Have you thought about that?
So Rumble supports S3 as a layer, and if you want to start querying something on S3 from Rumble, it takes 5 minutes. And these 5 minutes are mostly waiting for Amazon to set up the cluster. Once you have the cluster, you just do a wget of the jar of Rumble, and you can start writing queries against S3. Then the idea of Rumble is that, like a lot of database products, it pushes down as much as it can. So, for example, if you open a Parquet file or a root file or something like that, Rumble is going to push it all the way down to internally data frames and SQL queries, all the way down to Lorlin, and then it's handled by the parser that has the information that you only need to access dit and dat field, and then it only needs to read from the file system or from S3 what you actually need to read. This is all pushed down. So in the end, if you have an efficient implementation of the format reader that is orthogonal to us, then it will push down.
Thank you.
So I have an answer that is unrelated to Rumble. In a different project recently, we studied the use of serverless functions for data analytics, which maybe comes close to what you have in mind. So what we did there is to analyze Parquet files that are stored on S3, and we run this new thing called serverless functions, where you can spawn a number of functions, and in particular, you can spawn a number of functions that is in the thousands relatively easily and within just a few seconds. And we execute queries with these functions. And each of these functions fetches some of the data using the technique that Ghislain described, where if the data format supports it and both Parquet and root do that, it only fetches the bytes of the columns that are of interest. So each of these functions fetches the bytes that are necessary for the given query, does a computation, and sends the result back. And we actually applied that for a root file analysis use case. The paper hasn't come out yet, unfortunately, but we have submitted the camera-ready version. If you're interested, I can send it to you.
Absolutely, I would be very interested. Yeah, thank you.
Send me an email, please. I can't see your name. I only see the initials.
Oh, Carlos Malzahn at UC Santa Cruz. I will send you an email.
Great, thanks.
Thank you again for coming and showing us this interesting work.
Thanks for the invitation again.
Yeah, excellent talk.